Hello and welcome friends. Welcome to this new video. I hope you are enjoying the videos and the theorems on various topics which I am now preparing for you. Here I am in this video we will see more theorems on congruences. An important one of the results on congruences is if CA congruences to CB modulo n, then A congruences to B modulo n divided by D, where D is a greatest common divisor C comma n. Friend, in the previous video on the congruences we have seen that we can multiply the congruence by any number, but this video shows that to cancel out that number CA congruences to CB, then A congruences to B, to cancel that number, then the GCD of that the term modulo n will converted into n divided by D, and D is nothing but the GCD of the number C and n. So let us prove this result. It is given that AC or CA congruences to C into B. This means that by definition CA minus CB equal to K into n for some integer k. Then what is it is given that GCD, we can write it as, let us take C common. This implies that C into A minus B equal to K into n. GCD of C comma n equal to D. Therefore, D is a divisor of C and D is a divisor of n. There exists by definition R and S such that GCD of this R and S, two numbers are such that equal to 1 and C equal to R into D and n equal to S into D. Let us put this value here. You can see that what is a C? R into D into A minus B equal to K into n, S into D. dd will be cancelled, or we have R into A minus B equal to K into S. This implies that S is a divisor of R into A minus B. Now, by Euclid's lemma, either this S is a divisor of R or A minus B, but GCD of S and R is equal to 1. This means that this S is a divisor of A minus B, and therefore if S is a divisor of A minus B, A is congruences to B modulo S, okay, or A congruences to B modulo, what is my S? S is n divided by D. This proves the theorem. Now friend, we prove another important theorem which contains polynomial terms, and we apply the result of previous theorems. In the previous video we have seen where A congruences to B modulo n, then A raised to K congruences to B raised to K modulo n, where K is an integer. So if let P of X equal to Ck into X raised to K, K varies from 0 to m, that means it is of the type C0 X raised to 0 plus C1 X1 plus C2 X2 plus C m into X raised to m. I have expanded this. Be a polynomial function in x of x with integral coefficients. These c's are integral coefficient. If a congruences to b modulo n, a congruences to b modulo n, then p of a congruences to p of b modulo n. This is our statement. Okay, now what is given? Let us prove this. Proof is again very simple. What is the statement? Here a congruences to b modulo n. Then apply the sixth property, a raised to k congruences to b raised to k modulo n, where k equal to 0, 1, 2 up to m. Let us take this. Then again c raised to k, we can multiply by any number to this quantity by the third property, c raised to k. This is by sixth property, by property number 6 of congruences of that theorem. In the previous video you can watch that. If a congruences to b, then a raised to k congruences to b raised to k. Again if a congruences to b, then ac congruences to bc. This is our third property. Here we are applying the same property, ak congruences to ck into b raised to k modulo n. We can multiply by any number. But again if a congruences to b and c congruences to d, then a plus c congruences to b plus d. We can add the congruences. Okay, but how many these are? K equal to 0, that is c0 a raised to 0 congruences to c0 b raised to 0 modulo n. This is our first for k equal to 0. K equal to 1, c1 a raised to 0 a raised to 1 congruences to c1 b raised to 1 modulo n. K equal to 2, k equal to 2 c2 a square congruences to c2 b square modulo n. So these are the different congruences and we can add all these. Let us take the addition of this. We can add by this property of congruence. This gives us summation ck into a raised to k congruences to summation ck into b raised to k modulo n, where k varies from 0 to m. K varies for 0 to m. But look at the polynomial. What is this? This is a polynomial. This is polynomial in x. But when we put x equal to a, we get polynomial in a. So this is nothing but a polynomial in a, and this is a polynomial in b modulo n. Now important factor of this is that if we put x is equal to a in the polynomial, x is equal to a in the polynomial, and if p of a equal to 0, that means solution of this polynomial is a when modulo n, then we have this congruences to 0 modulo n. This gives us p of b congruences to 0 modulo n, right? That means whenever a is a solution of this polynomial, b is also a solution of the polynomial when a and b are in congruences. So this is an important part of these polynomials.